Welcome to our Chronom Deep Dive.
Great to be here.
Today we're going really small, diving into a fundamental piece of our universe, the down quark.
Tiny but mighty.
Exactly. And our guide for this is an essay by Jörg O. Schneeppert titled Down Quarks, Essenziellbaustein der Quantentechnologie.
Right. A really interesting piece.
So our mission today is to unpack Schneeppert's insights, looking at how down quarks shape matter and, maybe surprisingly, link up with quantum tech.
Okay, let's jump right in. So Schneeppert reminds us first, what are quarks? They're fundamental particles.
The absolute basics.
Yeah, the smallest building blocks we know. Think of them making up, protons and neutrons, the hadrons.
And these quarks, Schneeppert stresses, are governed by the strong interaction, which is, well, it's not like gravity. It's mediated by gluons, right? This incredibly strong force.
Super strong, yeah.
Yeah.
Especially at short distances. It basically glues quarks together inside those protons and neutrons.
And here's the really wild part. Schneeppert mentions you can't isolate a quark, ever.
Nope. They're always bound up. It's called confinement.
Confinement. Because that strong force just gets stronger if you try to pull them apart.
Exactly. Like an unbreakable rubber band, kind of.
Okay, so where do they fit in the grand scheme? Schneeppert puts them in the standard model.
Right, the standard model. Our best map, really, of all the fundamental particles and forces.
So you've got the matter particles, the fermions.
Which includes quarks and leptons, like electrons.
And then the force carriers, the bosons, like those gluons we mentioned.
Precisely.
And Schneeppert lays out the 6 quark flavors. Up, down, strange, charm, bottom, and top.
A whole family, each with different mass, charge, quantum properties.
But today, we're zooming in on the down quark, one of the lightest too.
And absolutely essential. Crucial for everyday matter. For us, basically.
So what's its specific role? Schneeppert highlights its charge, minus 1/3.
Minus 1/3 of the elementary charge, yeah.
Yeah.
Now combine that with the up quark, which is plus 2/3.
Okay, I see where this is going. Building nuclei?
Exactly. So a proton, 2 ups, 1 down, UDD adds up to plus 1 charge.
Makes sense. And a neutron.
1 up, 2 downs, UDD adds up to 0 charge. Neutral.
Wow. So just those two, up and down, in those combinations, that's the basis for protons and neutrons.
Which make up pretty much all baryonic matter, as Schneeppert points out. Stars, planets, you.
It really drives home how fundamental that down quark is. So why does Schneeppert emphasize studying it so much?
Well, it's key to understanding quantum chromodynamics, QCD. That's the theory of the strong force.
Right. Studying how downs interact helps us understand that fundamental force better.
Definitely. And, they're constantly being studied in big experiments like at the LHC.
The Large Hadron Collider, smashing things together to see what happens.
Pretty much.
Oh.
Probing their structure, how they behave under extreme conditions.
But Schneeppert also mentions connections to quantum computing and information. How does that work?
It seems like a leap, right? But the quantum rules governing quarks, these deep QCD principles, they can actually inspire approaches in quantum tech. Plus, Schneeppert points to down quark transformation, beta decay.
Where a down changes into an up.
Yeah, that's fundamental for understanding radioactivity and also neutrinos, a huge area in physics.
Okay, let's back up slightly and dig into quark basics again, following Schneeppert. Smallest known bits of matter, confinement still amazing, gluons holding them tight.
Yep, and that force gets stronger with distance, unlike others. It's weird, but true.
So the 6 flavors again with charges. Up, plus 23. Down, negative 13. Strange, negative 13. Charm, plus 23. Bottom, negative 13. Top, plus 23.
Those fractional charges are really key. Very different from, say, an electron's whole integer charge.
Still feels a bit counterintuitive, and Schneeppert mentions their masses are all over the place.
Massively different. From light ups and downs to the incredibly heavy top quark, like vastly different weights in the family.
And they all have spin 1/2.
Right, spin 12, which means they follow the Pauli exclusion principle. No 2 identical fermions in the same state. Crucial for matter structure.
And then there's color charge. Red, green, blue. Not actual colors, obviously.
No, It's another quantum number. It's the strong force via gluons really acts upon. And it dictates that only color-neutral combinations are stable.
Which leads back to protons and neutrons, baryons 3 quarks, and mesons quark-antiquark pairs.
Exactly. Always combining to be color-neutral or white.
So back to the down quark itself. That minus 1/3 charge Schneeppert emphasizes, it's not just some number.
No, it's fundamental, a cornerstone of the standard model, like you said, and how matter is built.
And finding experimental proof for these fractional charges back in the 60s, deep inelastic scattering. It's been huge.
Oh, absolutely. A Nobel Prize-winning discovery really cemented the Quark model.
Now, Schneeppat mentions the mass difference. Down is about 4.7 MeV up is about 2.2. Seems tiny.
It is tiny, but incredibly important. That small difference makes the neutron slightly heavier than the proton.
And that matters for nuclear stability.
Hugely. It affects which nuclei are stable and how elements form. If it were the other way around, the universe would look very different.
Wow. And these masses, Schneeppat clarifies, they're not measured directly.
Not easily. They're calculated, estimated using complex QCD theories. It's tricky.
Okay, interactions. Strong force, gluons, confinement, check.
Then the weak interaction. That's the one that lets a down change into an up. Beta decay.
The transformation mechanism.
Right. And then electromagnetism because it has charge, but it's much weaker than the strong force inside a nucleus.
And color charge ensures only those neutral combos, like protons and neutrons, are stable.
Precisely. QCD makes sure everything ends up to white.
So let's put them in the nucleus. Proton.UTED, a charge +1. The down contributes its -13.
Yep. And the neutron, charge 0. The two downs cancel the ups charge.
And Schneeppat highlights how the neutrons, with their down quarks, help stabilize the nucleus.
Right. They contribute to the strong force, holding things together, balancing out the proton repulsion. There's a delicate balance.
And that beta minus decay again. Neutron becomes a proton.
Ne plus E plus E. Underneath, it's a down quark, flipping to an up quark.
Du plus weak.
Exactly. Mediated by the weak force, specifically a W boson, which then decays.
And Schneeppat links this decay to, well, everything from how stars burn to radioactivity.
Yeah, it's central to the proton chain in stars, powers the sun, and it's the basis of much radioactivity, elements changing into other elements. It's everywhere.
Now, the quantum tech angle. Schneeppat connects understanding down quarks via QCD to quantum theory itself.
Well, QCD is a quantum field theory. Concepts like confinement or asymptotic freedom, where the force gets weaker at very short distances, these are purely quantum effects.
So understanding them deepens our grasp of quantum mechanics beyond the basics.
Absolutely. And Schneeppat points to quantum simulations, using quantum computers to model QCD.
To model quark interactions, that sounds complex.
Extremely, but potentially very powerful. We could simulate hadron structures, confinement, maybe even quark-gluon plasma.
That state from the early universe.
Exactly. Stuff that's really hard to calculate otherwise.
And are there other connections to quantum computing?
Schneeppat mentioned some deeper links. The math behind QCD, these non-Abelian gauge fields, has parallels in some quantum computing ideas.
Like topological quantum computing.
Yeah, there's inspiration there. And of course, experiments like the LHC are still crucial. They measure quark properties precisely, check Higgs boson couplings to quarks, looking for hints of physics beyond the standard model.
Which brings us to unanswered questions. Schneeppat notes we still don't fully get confinement right.
It's a huge open question. We know it happens, but a complete theoretical proof from first principles of QCD is still lacking.
And the exact structure inside hadrons and where quark masses really come from, still mysteries.
Big ones. These are driving forces in particle physics research.
Schneeppat also touches on theories beyond the standard model, like supersymmetry.
Right, which predicts partner particles for everything. So, a stare-down quark partner for the down quark, and string theory, potentially.
And could down quarks be involved in exotic matter states?
Potentially. That quark-gluon plasma we mentioned. Or maybe strange matter in neutron stars, involving strange quarks alongside ups and downs. Hypothetical, but possible.
So future research relies on bigger colliders, new experiments, astrophysics, and quantum simulations.
That seems to be the picture Schneeppat paints. A multi-pronged attack using all the tools we can build and imagine.
Well, this has been a fascinating deep dive into the down quark, guided by Jurgo Schneeppat's essay.
It really shows how these tiny particles pack a huge punch.
Absolutely. They're fundamental to matter, but also tied into the very cutting edge of quantum science and maybe future tech.
Yeah, the research keeps pushing boundaries. It's fundamental physics, but with potential real-world echoes down the line.
It really highlights that the exploration never stops. So thanks for joining us on this quantum deep dive.
My pleasure.
And a final thank you to Jurgo Schneeppat for the insights that framed our discussion today.